The broadcast is now starting. All attendees are in listen-only mode.
Good morning or good afternoon, ladies and gentlemen. We'll be starting the webinar in about 3 minutes, so please stay online and we'll start soon. Good morning and good afternoon again. We'll be starting in 1 minute. People are coming online now, so in 1 minute the webinar will start. Good afternoon or good morning again. Welcome to this webinar organized by Solarplaza on weather data and PV plant performance in Japan. Our first webinar dedicated to the Japanese PV market, a very exciting market to be active in. The speakers of today are three, including myself on the right-hand side. I'm Stefano Cruco. I represent Solarplaza in this webinar. I'll be moderating the session. We have two speakers, Mr. Pablo Cabeza of Vector 4 and Mr. Clive Lee representing Kip & Zonen, two leading global companies active in the PV industry and both active in Japan as well. Short introduction before we start with the presentations. About Solarplaza, most of us might or will know us. We are a global PV information platform for the solar industry, established in 2004. So far over 70 events organized in more than 20 countries, as you can see. And our network globally is over 60,000 professionals from representing the whole value chain, from investors, lenders, to installers and service providers. The webinar of today will deal with some specific topics. The title is dealing with weather data in Japanese PV project performance. Weather data is well, worldwide a very important topic in establishing cash flows, return estimations for PV plants, but also during operation to be able to benchmark performance, etc. So three topics, three issues we want to discuss are, as you can read on this slide, how does correct use of weather data enable more precise revenue forecasts, differences in application of weather and specifically irradiation data between Japan and other countries worldwide, and we'll dive into the top three or maybe a couple of more pitfalls in dealing with pyranometer data. First speaker of today will be, as mentioned, Mr. Pablo Cabeza. He's in the engineering department in Japan of Vector 4, a company of Falk Renewables. Pablo performs feasibility studies and technical due diligence. So far he has done that for over 1 gigawatt. In Japan he has led yield assessments for over 300 megawatts, and well, previously he has worked at Airbus in Spain and the Spanish Economic and Commercial Office in Tokyo. Mr. Clive Lee is customer service specialist at Kip & Zonen, as mentioned before. He advises on all Kip & Zonen products and applications and all the issues and questions that can come up on those during operation. He's also involved with all aspects of solar radiation measurement in meteorology, climatology and renewable energy. And previously he worked at Siemens Environmental Systems in the UK. This this webinar is part of the preparation towards the conference we are working on, taking place in Tokyo in about 3 weeks, 2 and 3 June. The conference is titled Solar Asset Management Asia. It's the second edition. It's a 2-day conference with around 30 speakers. We expect over 200 participants and about 10 sponsors. Just for your information, a couple of speakers are shown here. They include METI, Takara Leben, Bloomberg New Energy Finance, Shinsei Bank, First Solar, Pacifico, Next Energy Holdings, Electris Japan, Solaris, and many more, as you can see here. The conference topics will include the new O&M requirements that will be there, PV plant performance, O&M asset management strategies, but also hugely important topics in Japan like curtailment, what is happening with infrastructure funds and what is the future of this, secondary market activities, portfolio management and strategies for the future, how to deal with 24 yen per kilowatt hour projects or lower or no feed-in tariffs in the future. A big thank you to the sponsors confirmed so far for the conference. We still have companies attaching their name to the event, but so far I want to briefly highlight the sponsors that will be at the conference in June. Back to the webinar that will start now. A few practical notes. On the right hand side you see a chat box which enables me but also you as participants to ask questions and also to bring up any technical issues you might have. So please feel free already during the presentations to ask questions written. I'll be asking these on your behalf after the presentation, so at the end of the webinar. You can also write in Japanese because we have a colleague here that is supporting and will translate these, so we can ask all your questions. If we don't get to them afterwards, we might be able to send these to the speakers. Another interesting thing, we will have poll questions during the presentation. So questions come up and you can answer them quickly by clicking your opinion. These are anonymous questions, and it's nice to have some input from your side as attendees as well. So I hope you can collaborate in that and give quickly your thoughts so we can react to that. First speaker again, Pablo Cabeza, Japan Engineering Department of Vector Quattro. Pablo, I'm going to unmute you now and make you presenter. So we can now hear you, and you now have the request to share your screen. Feel free to go ahead.
Okay, give me a sec.
Sure.
Okay, so do you see it correctly now?
Yes, it is well visible, so please go ahead.
Okay. Okay, thank you, Stefano, for the introduction. Ladies and gentlemen, good afternoon here from Japan, from Tokyo. I'm talking here on behalf of Vector Quattro from the engineering department, and as Stefano was introducing, I'm going to talk about the importance of weather data in estimating PV projects' performance. This presentation will take around 15 minutes, and after a brief introduction, I will talk about the importance of the weather data, the databases that we usually have here in Japan and we use, the advantages of a correct use of the weather data, and I will finally dive into the particularities of Japan compared to other locations around the world. So first of all, a brief introduction. My two main topics will be how does the correct use of weather data enable a more precise revenue forecast, and the difference in application of weather data between Japan and other PV markets. As you all know, weather data is of the utmost importance, either if we are in a pre-construction phase or projects are already operating. It is important to estimate how the plant is going to behave in the following years. So we need to know the site-specific conditions. Now, site-specific conditions, I have here a small graph. As you can see, in Japan we have more than 10, actually 11 different regions so established by the Japanese Weather Association. And Japan poses new challenges. It's not a market, it's a new market. All the characteristics that were, let's say, old school in Europe, countries like my country, Spain or Italy, have traditionally been thought as better for solar installation. And what about Japan? Japan is a place where it rains more, where we have alpine locations, we have volcanic conditions in other places, so we need to pay more attention to the weather conditions. Now, when we go to the weather conditions, we need to really understand what are we talking about. This will be the weather variables. What might come to everybody's mind will be the irradiation and the temperature. Higher irradiation leads to higher yields. Higher temperatures leads to poorer performance due to the PV modules. All these things need to be taken into account. How do we take these things into account? We are going to create a typical year. Forecasting from one day to another is good maybe for taking your umbrella every morning. But when we look to a PV project, what we need to do is forecast 20 years of the plan. For doing these things, what we are going to look is 20 years on the past. So a typical meteorological year is actually the average of several years, usually 20 or 25. And 25 years of data are not usually available in the place where we're going to install our project. We might have a location nearby, or we don't have a location nearby, or we need to use satellite databases. So if we can launch our first poll question, please.
Yes, we're bringing that up now.
Okay, thank you.
So here's the first poll question. Pablo, feel free to read it up. Can you see it as well?
No.
I'll be reading. So within 20 years, how different can be the maximum value recorded for irradiation from the minimum one? So what is the maximum difference within 20-year data? This is within 5%. Do people think this is between 5 and 10%? And you can already click and vote. Is this between 10 and 20%, or well, even more than 20%? So if everyone can give his or her answers now, that would be great. Is within 5? Do you think this is within 5%, between 5 and 10%, 10 or 20%, or even more than 20%? There's no right and wrong, just your estimation, and we'll see what people think. Yeah, okay, let's have a look at the answers that we can see here. Pablo, can you see the answers as well?
No, I'm afraid I cannot.
I can tell you. So 60% of the people that responded think this is between 10 and 20%.
Okay.
And around 35% thinks this is even more than 20%. So people think this is varying a lot. Let's see what you have to tell us.
Sure. So well, continuing a little bit with this slide before moving to the answer, as you can see, we have different databases, and all of them give different values. So what do we need to do? We need to minimize the error. What errors do we make when estimating or when forecasting irradiation, basically, or other weather data? Basically, there are two. One is the error of measurements, the error of the equipment. And you can see here in the first graph that we have confidence intervals about where the measurement is, and depending on the equipment we are using and depending on the distance where we are measuring compared to the project location, this error will be higher or will be smaller. And there is another error associated with dispersion, and it's the answer to the question. So we have here a graph of 20 years in a Japanese location. This is measured with a good pyranometer, state of the art, and as you can see, from year to year, it is quite funny how the irradiation goes. So actually, in this location, between the minimum and the maximum, we have more than a 20% deviation. And this is not only a particular site. I picked it quite randomly because it's something that we have in Japan. Now, bringing back the topic of the typical meteorological year, why do we consider 20 years? Because in 20 years, with the 20 years that we measured in the past, we can potentially reduce this dispersion error to 1%. So it's almost eliminating this error and only taking the error of measurement. Now, as I was saying, decreasing the uncertainty, decreasing the errors. Why do we need to do this? Because we need to have a good estimation. So we need to go case by case because databases are different, because locations are different. The dispersion is more than 20% in some locations, 30% in some locations, can be a good place, and we might have maybe 10% dispersion. So our PV project might be located in one of these 4 squares. So we can be using a good database with a low dispersion error, so we will have optimum conditions. But hey, this would be too easy. Here in Japan, usually we are in one of the green squares. We have either low database error but high dispersion error because we don't have these 20-year measurements, or we might have a good track record, but the uncertainty, the error that we might be making with the database might be high. So our advice would be very simple in these 2 cases. Either comparing with another databases to see how other inputs are, or compare with longer periods. We go to a station with a higher period of track record, and we compare both things. Of course, if we are in a place and we know that we have high uncertainty and high dispersion, we should be doing other thing and potentially thinking of another methods.
Pablo, a short question before you continue. Someone is asking on slide 4, what do you mean with ORL? Can you briefly explain slide 4?
Yeah, ORL is a database here in Japan. is a satellite database here in Japan. I will introduce it in a couple of slides, if you don't mind.
Okay.
Okay? Sure.
Yes, absolutely. Please go on.
So, moving ahead, here in Japan, Japan is a developed country, and Japan has installed several weather stations throughout the islands. So, top chart, top graph, we see a lot of weather stations. What's the bad thing? Not all of these have pyranometers. Not all of these have actual equipment that can measure irradiance. Traditionally in Japan, the two references have been NEDO and the Japanese Meteorological Agency. So, well, I was going to launch the second poll question. Which are the databases people use here in Japan? Which are the databases they know?
Okay. Thank you, Pablo. I'll read it up. So for the people in the webinar, please let us know your anonymous input. Assuming you're involved in Japan, or if you're involved in Japan, do you use NEDO? Do you use Metronorm? Do you use both of them and others? Or do you use other databases? So if you can just let us know your experience with this, Pablo can reflect on that moving forward. So we will give the people 5 more seconds. Okay. Let's see. Okay. So the answers, Pablo, I'll read them up.
Yeah.
35% of the people say they use NEDO. 13% says they use Metronorm. 42% says we use both of these. And 10% says we use other sources. So
okay.
Yeah, so I'm curious, does it match your experience? Is that reflecting the market?
Yes, actually. So, yeah, most of the answers go to NEDO and Metronorm. I have briefly here introduced both of them and other databases that are well known and not so well known as the question was launched. So here in Japan we have NEDO. NEDO is doesn't need much introduction. It's a terrestrial database that uses pyranometers in certain places and weather stations where they use a weather algorithm to interpolate the radiation. They basically measure the sun hours and give up a number. Metronorm uses pyranometers and satellites in some places also introduce satellite data and interpols the places here in Japan either with only the pyranometers or with the satellite as well. We also have 3 satellite databases. One is NASA, another one is OREL, that is a satellite database developed here in Japan that uses Japanese satellites, and it has a pretty decent track record, already more than 10 years. And we also have SolarGIS, which is a database that's well used throughout America, in particular Mexico, South America, and also in some places of Europe. And SolarGIS can also be used in Japan. I'm not saying these 5 are the only databases you might use. There are more. I'm just presenting some of them. So when we use them, what we need to do is to consider the particularities of each one of them, going and looking around its particular site. We need to know the uncertainty they have and how they work. So we conducted, as the poll also reflected, all these results that I was expecting. Metronorm and NEDO are the top 2, let's say. Everybody knows them, or practically everybody use one or another, or both. So what we see here is NEDO has all these orange spots throughout Japan. But please remember, not all of them use pyranometers. And Metronorm has these green spots. All of these, there are pyranometers. Good points of NEDO. You will have a NEDO station very close to your site. Good points of Metronorm. You have pyranometer data and let's say consolidated algorithm of interpolation. So if we compare both of them in places where they have pyranometers, they both practically match. If we go to another places, we can see that they have slightly different. In the coastal places, we might have a 2% deviation. In flat areas such as the Kanto Plateau, we might have 5% deviation, and in mountains we might go up to 12% deviation in average. What do we see? That metronome is generally over Nedo. Why is this? Nedo uses data starting from 1981. A metronome is more recent, it started in 1990. These 10 years of difference might seem little thing, but let's say we're poor irradiation years in Japan, so this pulls the Nedo value a little bit below. And also that due to the interpolation that metronome uses in the mountains, it introduces some variability in the result that also needs to be taken into account, especially in the mountain regions, as I was saying, because in the coastal places we have pretty similar values. So I will move ahead to the advantages of using correct weather data. Main advantage: providing a more reliable number in the yield estimation. During the design phase, we need to know how the plant is going to look like in the future. If not, we'll just stop developing the project. So, taking into account the irradiation that we are going to have, taking into account the temperature that we are going to have, and particularly in Japan also, taking into account the snow that might fall in the project, we can help in finding the most efficient design or the configuration that will maximize the produced energy. These two might look similar, might look very alike, but are different. Here in Japan, usually everybody goes to the second one, maximize the produced energy, even though it's more expensive and not so efficient. Everybody has a different model. So what do investors seek? Profitability and revenue. They look for money. So what do they need? Accurate weather values to know how the investment is going to go. What do usually lenders look for? Reduce risk. What do they need? Optimize uncertainty and different timeframes. So here we need to close the gap between the P50 and the P90. And this is why it is important to reduce the uncertainty of the databases that we are using. We need to understand what is the uncertainty we are introducing in our assessments and how to diminish it by comparing it with other databases, by combining databases, etc. Other times, we might have on-site measurements. We have a project under operation already, and we want to forecast how the future will go with the data that our pyranometers are already measuring. This is a good thing, but we need to take into account that 1 year doesn't reflect the 20 years. If you remember the previous funny graph with the more than 20% deviation. So what we need to do is extrapolate these values to a longer period. Extrapolate is gaiso in Japanese if everybody needed it. So we need to implement a little bit of mathematics in here, but it's something that is also useful and something that we can do. So now, let's go to Japan. Japan's particularities. Japan, as I was saying, has 11 different climate areas. If you can see here at the same latitude, we might be crossing more than 4 different continental climates. This is something that in such a short frame of space, in 100 kilometers, we might be crossing 4 different places. I haven't seen this only in Japan, in my experience, and it's something that needs to be considered as well. Only by moving 20 kilometers to the west, we might be in a completely different region. We might be in the other side of the mountains, and let's say west of Japan, during winter time, it rains a lot. Kanto, during winter time, it rains quite fewer than the rest of Japan. It's shadow rain effect called. very funny in such a small country. So, what has been traditionally happening here in Japan? Due to this extent databases that they have, these Japanese databases have been traditionally trusted by local Japanese developers, by local Japanese financing entities, which is good, but also has the effect of blinding other possibilities. We need to understand that this Japanese database is not always perfect, and we need to understand that international practices are also applicable in Japan. So we might be considering satellite databases, even if they have a shorter period of data, but we might use them for understanding how the deviation is in these last years. We might use them to have a better point resolution of all the places. We've seen here in Japan, in our experience, places overall in Kyushu area, where between one ground station and the, let's say, following the closest ground station, separated both of them 18 kilometers, the difference in irradiation was more than 21%. So what happens if our project is in the middle? Which one should we rely on? We need to use maybe satellite databases to assess this difference. And of course, and as I have been saying several times through this presentation, there are also places where the snow needs to be considered. And when I mean snow, it's not just a little snowfall during winter time. I'm talking about more than 1 meter of snow depth during 3 months in winter. So maybe, Stefano, we should be launching the last poll question, as I will introduce also the importance of the diffuse component here in Japan.
Yes, there we go. I'll read it up, Pablo. Give me 1 minute. So the question is, what is the percentage of diffuse irradiation in Japan compared to global irradiation? Is that half of it? Is it 1/3 or is it 1/4? So can you elaborate on the question, Pablo, just for people to make sure they understand it correctly?
Sure. When talking about irradiation, usually what we measure is the global horizontal irradiation. Mm-hmm. But this irradiation is also divided into components, direct and diffuse. So I want the people, if you can have a quick look to this picture that we have here. Imagine that this green module receives direct light, reflected light, and scattered light through the atmosphere. So this is called mainly diffuse. How do you think this diffuse component, how important do you think it is in Japan?
Compared to global. Okay, yeah, people are voting now, so let's give them a couple more seconds. Do you think this is half, 1/3, or 1/4? Let's have a look. So Pablo, about 30% thinks this is half. The majority, 45%, thinks this is about 1/3, and 24% thinks this is 1/4. So let's share with us what you think.
Sure. Well, actually, when you compare both of them here in Japan, you go to see that diffuse component is half of it, which is actually funny, because half of diffuse component is seen only in northern Germany and places like that, which are much more in northern location compared to Japan. South of Japan can be compared to Mexico, where we have only 1/4 of diffuse component. North of Japan can be compared to Italy, Spain, where we might be around 1/3. So why is this important? This is important because the diffuse irradiation, if we don't have good measurements of it, we are going to introduce more uncertainty when we perform our yield simulations. And not only just a little. I'm talking about percentages of maybe 4-5%, which obviously will have a deep impact into the revenues. And well, basically, I think this is all from my side. I would like to thank you, everybody, for your kind attention, and looking forward to your questions.
Thank you very much, Pablo, for the presentation. It's always interesting to present in front of a screen, I know from experience. Very interesting presentation. Before we go to the next presentation, I'll take now time for 2 short questions, and we'll do more questions later in the webinar. Very simple questions. Are the databases, accessible by public, Pablo, in Japan?
Yeah. Some of them are accessible to everybody. I mean, Neto is public. I think it's one of the big reasons it's so popular. It's free. It's pretty easy to use. Everybody can understand it quickly. The only, let's say, weak point for us foreigners here is that it is in Japanese, but once you get used to it, it's pretty simple to use. Other ones are usually paid, especially Meteonorm, SolarGIS, Sorel. NASA is also free, but it's hard to use it in Japan.
Okay, clear. Another question, you just mentioned that combining databases and data is important to reduce the uncertainty. To what level of uncertainty can you get by combining 2 or more databases? Can you share that?
Well, it will depend in the end of the uncertainty for the specific location. When you use the database, you will have, as I was saying, 2 errors. One due to the dispersion, to the variability of the database that will be reduced throughout the time, and one of the, let's say, basic error. So this is the one that you seek reducing when you combine databases, because once you have a long period, and if you combine similar periods, you cannot combine 20 years from now and 20 years from the start of 19th century, sorry. You need to match these periods. Once you can do it, things that were up to, I would say, 8% can go around 5, even 4% if you combine several of them. So it's a good approach, we believe. Yeah, I can say there is one paper. I don't remember the name now. I can show everybody. I will show everybody. I can show the title later. Yeah, I can share it.
Okay, Pablo. Last short question for now. With the rest of the question, we come back later. How do you assess snowfalls? What is your approach?
Well, for assessing snowfalls, as I introduced, there is a pretty decent network of stations throughout Japan, and these are public. Snow data is easy to get in Japan. So you need to understand. You need to look for the snow recurrence. How long does it take? But you also need to consider other parameters as temperature and humidity. So once you get all these things, you can put it into a model. We've developed one ourselves in order to do these estimations. You put it into a model and you can come up with some numbers. I hope it answers.
Yeah, if people have more detailed questions about it, we will address them to you also later by email.
Sure.
Pablo, I'm going to mute you for now. If there are other questions later, we'll get you back, and we will move to Clive. Let's see if we can hear Clive. Clive, go ahead. Are you there?
Yeah, I'm here, Stefano. Yeah.
Perfect. We can hear you very well. I'm going to make you presenter now. So make sure you have your slides ready, and the floor, the online floor, is yours.
Okay. So welcome everybody. Thank you for joining us. And so can you see that now, Stefano?
Yes, we can see your screen.
Oh, okay, that's cool. So following on from what Pablo was saying, a lot of the most reliable data for solar energy resource assessments is coming from pyranometers. And also, of course, they are used in real time for assessing performance ratios and efficiencies in operating plants. And the question is, how reliable, how uncertain is that data? So that's what we're going to have a look at now. And you heard that Pablo was talking about uncertainty rather than accuracy, and there is a reason for this. Accuracy doesn't have an actual firm international definition, and most organizations, such as International Standards Organization, World Meteorological Organization, only refer now to uncertainties of a parameter under specific conditions. And in general, that means at the 95% confidence level, which for a standard deviation of 2 in a normal distribution. So typically it's 2 standard deviations. And most pyranometer specifications are also given to that level, either as a maximum, a minimum, or at the 95% confidence level. And you can then, of course, effectively get an overall uncertainty of several parameters by taking the root sum square. So you take the square of all the individual uncertainties, add them together, and then take the square root. So for solar radiation measurements, as most of the data that is around, as Stefano was saying, is measured with a horizontal pyranometer, a thermopile type pyranometer, and is measuring the global horizontal irradiance in watts per square meter, which then might be summed over hours, days, months, or even years to get the total energy available. So at the moment, we're talking here about the actual specifications, performance of the pyranometer, and we're assuming that it's been correctly installed and maintained, often not true. We're also assuming that the data acquisition system is not going to degrade the measurements, which is also quite often not true. But we'll come back to that later. Now, if we're looking at definitions of what we mean by the uncertainties, there is a standard, which many of you will be familiar with. It's ISO 9060-1990, specification and classification of instruments, and that includes pyranometers for measuring global horizontal irradiance, or indeed tilted, and also pyrheliometers, which are the instruments that measure the direct sun when mounted on a sun tracker. And that standard defines actually the characteristics of a pyranometer. And it actually, for different classifications, different qualities of pyranometer, it specifies the maximum allowable changes and deviations you can have with environmental conditions. So the lowest category, the lowest classification is second class. And as we move up, getting a little bit better, we have first class. The best one's a secondary standard, but there is nothing higher. There is no primary standard pyranometer. It's actually done by measuring diffuse and direct irradiance and calculating the global using the solar zenith angle, how far the sun is away from vertical above. There are certain reasons for that. So secondary standard is the highest classification, but because it's quite an old standard from 1990, it actually means there are many instruments that are better than are required for secondary standard. So they go up above, well above what is in the actual ISO standard. So here we have a list of the parameters defined in ISO 9060-1990 that have an effect on the measurement. So there's the response time to a 95% step change, 0 offsets, these are thermal ones related to energy exchange between the atmosphere and the instrument. It's a thermal instrument. Then the response to rapid temperature changes, 5 degrees per hour, non-stability over a year, so drift in the sensitivity, non-linearity, so that's reference to 500 watts per square meter as a typical calibration value, as roughly in the middle of a typical measurement range for most locations. And the directional response, So when the beam is from the sun is moving from directly overhead, which is the normal calibration condition, down towards the horizon, how is the pyranometer responding to that? Is it actually following the, shall we say, desired response, which actually is notionally a sort of cosine function, at least up to about 5 degrees above the horizon, 85 degrees zenith angle. Then the other functions we have are spectral selectivity. So this is how even is the response of the pyranometer to radiation in the wavelength range from 350 nanometers, 0.35 microns, up to 1,500 nanometers, 1.5 microns. Roughly 90% of all the energy from the sun is within that range. And that is a range that can be covered quite easily by normal standard optical glasses. It's specified that actually a pyranometer should measure from 0.3 microns, 300 nanometers, up to 3 microns, 3,000 nanometers, because 99% of all the irradiance is within that range. However, it doesn't have to be completely flat, even response over all that range, just the key part in the middle. Then we have temperature response. That's an important one. So when you deviate from the calibration temperature, which is typically plus 22 or plus 25 degrees, something like that, indoors in a laboratory, what is the effect that it has on the sensitivity of the instrument? And this is often one of the largest effects. And you can see for a second-class pyranometer, you're allowed to have up to 8%, plus or minus 8% deviation over a 50-degree temperature range, which is actually quite a lot. That's typically what you have for an entry-level model with no temperature correction. To get to a first-class one, better than 4%, you need to have some temperature correction in it, and then better again for a secondary standard. And then the tilt response, actually in a good design of pyranometer, this is minimal, but it's calibrated horizontally. What happens if you tilt it? If you like at the angle of the panels, plane of array, right round to vertical. It does have a small effect. So all of these things can be quantified. But in order to find out what effect this is going to have on a site, you need to know the local conditions. And if you're going to apply it generally, one of the things we can do is to define, shall we say, a standard day. So we could say, okay, a standard day for mid-latitudes, and we can have a range of solar elevations, so zenith angle. We can have a range of temperatures and say, okay, we don't expect that it's going to change much between, say, limits of minus 10 degrees and plus 40 degrees. That's our 50-degree range. If you're in mid-latitudes, the sun will never be directly overhead, of course. And so we can actually convert all the figures and parameters that are in the ISO standard into deviation change and changes for this typical day that we're going to consider. And then we can use the actual real figures that are for the pyranometers, not the ones in the standards, but the actual real defined measurement ones. And so we can then come up with something like this table. So we can take all those parameters that have an effect. The response time is not significant in this case because we're talking about daily totals, daily uncertainties. And then we can see that for the different categories of pyranometers, what the actual effect is. And we can see that we can come down to at the bottom here, but okay, you have a slight increase in uncertainty when it's tilted, but not very much. And generally, that if you have an entry-level model, a second-class one, like our CMP3, which is a passive one, it just gives you the direct thermopower detector output, then you have an uncertainty over a day pretty much anywhere at any time, mid-latitude conditions. So this is pretty much a worst case of 5.7%. If you have the smart one, which has microprocessor inside and that has temperature correction, it's better, 3.7%. Then we go up to the first class, CMP6, again, a passive one with no electronics inside it. It's a little bit better than the CMP3, 4.7%, percent. And then we go up to the secondary standard ones, and we can see that these have temperature correction, they have a much better detector, they have better thermal characteristics, and it gets to within about 1.6%. Then if you go to the very expensive top-level research, grade 1, which has different type of construction, quartz domes and such like, it gets better again. But that's rarely used in solar energy applications, more in climate research. So those are the figures that you could expect to achieve pretty much anywhere at any time.
Clive, there is a question. If you could go back to your previous slide, and I would like to ask it now. The question that someone has asked is, could you elaborate on the surprisingly low temperature error for good quality pyranometers? Is there an internal correction? If yes, how does it work? Or will you come back to that, by the way? In a minute, so.
we can do that now. And this is inherent not just to Kippen-Zonen pyranometers, but all types of thermal detection ones that use thermal piles. That essentially you've got a large number of dissimilar junctions. They may be dissimilar metals working like a thermocouple, or they may be dissimilar types of semiconductors that are actually working more like a Peltier device, which is in the more expensive ones. But there is a change in the sensitivity with temperature, because the physical dimensions are actually changing of the junctions and the thermopile. And as standard, the entry-level models like a CMP3 or indeed the CMP6, you just have the raw output from the thermopile. Radiation comes in, heats up the black surface, that gets warm, the other side of the thermopile is in the housing, connected to the housing, so you have a heat flow that goes through, and that generates a very small voltage, a few millivolts coming out. That changes with temperature. Now, that is not corrected on the entry-level models. It's just whatever happens. And over a 50-degree temperature range compared to the calibration temperature, say 20 degrees, that might change by 5%, the CMP3. In the case of the SMP3, same detector, but it's got a microcontroller inside. It measures the temperature and it corrects for it, and it comes down to 2.5%. But there is considerable variability in the entry-level type of detectors. When you go up to the secondary standard one, which, as I said, is a sort of more like a Peltier ceramic device, is much more stable with temperature, and it's also much more predictable. So they either have a passive network, temperature correction network. There's a thermistor, an NTC, and some resistors, and it applies a correction, and that gets it within the 1% temperature response. The smart ones with microcontroller, they're the same thing, but over this temperature range, there's no significant difference. If you look over a wider temperature range, so if you go from minus 40 degrees up to plus 70 degrees, so for instance like in a very hot desert situation, then you will see that the smart ones with the microcontroller, they have a better correction at the limits, and that's because the function is not linear. It's a third order polynomial. The passive correction with components inside is linear, but inside the smart ones is polynomial, so it gives a better correction over a wider range. So basically, that's where it comes from. This is one of the biggest sources of error.
Great. Thanks for answering that in between, Clive. Let's continue with the rest of the presentation. I see other questions coming in, but we'll deal with them afterwards.
Yeah, okay.
So let's feel free to continue.
Okay, so what we're talking about there is relative variations, relative uncertainties. So compared to what it says on the certificate, the sensitivity that is on the calibration certificate and on the instrument label. Now, of course, we're assuming that it's got a valid calibration, and normally we recommend recalibrating every 2 years. If people are interested, we can come back later to why that is the case. But there is also an absolute uncertainty. So every pyranometer has got a calibration certificate, and it's traceable back to the World Radiometric Reference in Switzerland, at the World Radiation Center in Davos. And of course, transferring a calibration from the world radiometric reference to our reference pyranometers that we use in production. There is an uncertainty, and then there is an extra uncertainty calibrating the production ones in the factory. And this is typically, these are getting better because techniques are improving, but this is basically what it is. An exact value for the individual pyranometer is on the certificate at the 95% confidence level. So again, if you have a secondary standard one, a typical one, the most that are used these days, at least in Europe and in North America, are secondary standard pyranometers. You've got an additional absolute calibration uncertainty of 1.5% as a root sum square to be added. So typically what it means is that as an absolute value, you should be able to get within 2% over a daily total, compared right back to the world radiometric reference, with a secondary standard one that is clean. And this is the key thing. This is where a lot of errors come in, is that it doesn't need an awful lot of dirt on the dome in order to greatly reduce the amount of radiation that's being seen by the detector. Dew in the morning, raindrops absorb and scatter the light. Frost, of course, very reflective. A lot of places you have problems with dust, dirt, sand blowing around. They may be dry environments, but it may be also from fields, agriculture in the summer. If they stick on a damp dome, that's very difficult to remove. Dew in the morning and then dust blows across it, and it can form almost like a cement, a hard layer. And in many areas, of course, you have atmospheric pollutants. It might be near to industry or petrochemical plants, which affect the spectrum of the light. And a lot of places do not have people who regularly go and clean everything. It might be only every 2 or 3 weeks, perhaps. Okay, so here's our first question for the poll. How much do you think morning dew or raindrops will reduce the irradiance reading?
Thank you, Clive. So I'll repeat the question, but how much do you think morning dew or raindrops will reduce the irradiance reading? And for the people listening to the webinar, please let us know what you think. This is 5%, this is 10%, this is 20%, or over 25%. So how much does this affect? And let's see what Clive has to tell us. I'm checking if people are already voting. We'll give you a few more seconds. So how do you think morning dew or raindrops will reduce the irradiance reading? Okay, Clive, I'm not sure if you see the answers, but I'll read them up.
No, okay.
17% of the people thinks this is only 5%. 1/3 of the people, 33%, thinks this is affected by 10%. 36% thinks this is 20% reduction, and 14% thinks this is over 25%. So opinions are different. What is your experience? Please go ahead and share with us.
Okay, well, actually, yes, that last group is correct. It is nearly always over 25%. Even
over
if the
25%.
Yeah, more than 25%. Because even if the dome is clean, most of the drops only roll off on the vertical sides of the dome, and they still sit on the top until the sun has evaporated them off. If the dome is a little bit dirty, then actually the drops will not roll off and they stick there, and it will be even bigger, and it can be up to 40% if you have a dirty dome and a lot of the raindrops are sitting on the top of it. So yes, at least 25%. And so this is a good reason for keeping the domes clean, because otherwise you just have to wait for the sun to come up, and on a cloudy day it may take a very long time before dew or raindrops are evaporated off. So one of the things we can do is fit a ventilation unit. So what this is doing is having a high flow of swirling air. There's a cover fitted that you'll see in the next picture, and this airflow goes over the dome, and it's forming like a barrier layer, and it does two things. One is it evaporates raindrops. It stops dew actually forming, and it makes a little barrier level to keep off particles, sand, dirt, dust. And because the dome is always dry, they don't stick to it. So it means that you can keep the dome clean for a much longer period. And here's a picture with the cover on. It also helps to stabilize the temperature of the instrument, which reduces some of the thermal offsets, which does have a small effect and maybe another 0.1% improvement on the uncertainty. There's heaters inside you can turn on if it gets cold. It can melt, frost and snow. And so the real benefit is you get better quality data for more of the time, and particularly in the morning if there is dew and after rain. Then the other thing is we've been talking about horizontal measurements, GHI. And typically the pyranometer has a clear view of the whole sky, the direct sun throughout the day, of course, but what happens when we tilt it in the plane of array of the panels? So this is typically what is being done to measure efficiencies, plant efficiencies, array efficiencies, performance ratios. It's tilted. One of the problems is you don't see the complete diffuse sky anymore. And another is that the pyranometer can partly see the ground and whatever is in front of it. So here's a picture, one horizontal and one tilted. And this is quite typical. And you can see from the picture the tilted one can see the backs of all the panels in front and all the array frames. And this can have some strange effects. So here's our next question for the poll. Do you think a tilted pyranometer in the plane of array, like in that picture, will read higher or lower than the horizontal one?
Thank you, Clive. Let's give the participants some seconds to answer. So do you think a tilted pyranometer will read higher, lower, or maybe equal as a horizontal pyranometer? So let's see what people think. It seems interesting question. Few more seconds. Okay, so the vast majority, Clive, 67% thinks this is higher. Only a few people think this is the same, and 1 in 3 thinks this is lower. So yeah, it could be both. Tell us what is real.
Okay, well, generally speaking, most of the people are correct. But if you've got reasonably bright, clear sky, generally the tilted one will read higher. In the type of installation picture that I showed, which is typical. And the reason for that is that you often get reflections off the top of the panel frames and the supports. There may also be reflections coming from other supporting structures around. And although the view of the rear of the panels are typically dark, but the ground between, and it depends on the spacing of the arrays, has an albedo. It's partly reflective. If it's grass, it's reasonably low, but if it's concrete or snow on the ground, then it's quite high. And that will increase the readings. But it might change during the day, but depending on where the sun is and the layout of the particular plant. The only time typically when it might read the same or maybe even slightly lower than the GHI one is actually when you've got a completely cloudy diffuse sky, because in that case it's missing seeing part of the diffuse radiation from the sky, and there is no significant direct radiation reflecting off things. So if you've got a completely diffuse cloudy sky, the tilted one will normally read lower, but when you've got a reasonable amount of bright sunshine, it will normally read higher. So one of the important things though is here's a pyranometer with its, and you can see the dome, black absorber surface. It can't see anything coming from below its horizon, below the black detector. Anything above that, it will see light from. So it's important that if you're mounting it in the arrays, which is very common, like this, that it needs to be a few millimeters at least above the frames and the panel surface, so you don't get any light reflected into it. And another way of doing it, though, is not to measure in the arrays, but actually to measure all the tilted irradiation that's coming onto the plant. So you mount the pyranometer in front or behind, it doesn't matter which, but so they're not interfered with by the arrays. They don't see any light effectively reflected from anything. You get the free field, shall we say, incoming tilted radiation. And this gives you a better measurement, but of course it's measuring all the energy available to the site, not what is seen by a typical panel. So it's a slightly different way of doing the measurement. Now, there's one other issue here, that we said we don't want to degrade the measurement of the pyranometer by our data acquisition system. We said that we can get within 2% or better for a daily total with the secondary standard pyranometer in an absolute measurement. But often industrial data loggers that are used with analog to digital converters, input amplifiers, etc., actually are not that good. Most of the ones that cost a few $100s, they could have an uncertainty of 5 watts per square meter. And that is over the whole measurement range. So 5 watts per square meter in 1,000 on a bright sunny day is not so significant. 5 watts per square meter in 100 on a very cloudy day and when the sun is low is significant. So there are many cases where actually the performance, the measurements from the pyranometer are being degraded by the digital system having analog to digital converters built in. When we have these smart pyranometers, that's all done inside. The analog to digital conversion and all the conversions into watts per square meter are done inside the pyranometer, and then what you get out is a digital value in watts per square meter. So as long as you store it, then it's not being degraded in any way. The other thing is the measurement frequency. A lot of older PV plants typically only take one measurement every 10 minutes. And the problem with this is that if you've got a partially cloudy sky, if you take your measurement when the one cloud is in front of the sun, it's very low, but it does not represent the whole period. Similarly, if you take a measurement when there is one gap letting the sun through in a cloudy sky, it also doesn't represent the whole period. So it's strongly advised to sample at least every 10 seconds and then store 1 minute averages, because then you can have good quality data that you can use for your real-time performance measurements and such like. There's no problem these days with having plenty of data stored, but if you haven't stored it, you can never go back and improve the measurements. Typically in systems that we install, we actually sample every second, and we store every minute the average, the minimum, the maximum, and the standard deviation. And with that information, you can do some real statistics. So, in the end, it comes down to we've got some numbers representing the irradiance, and it's the whole measurement chain that is important, not just the pyranometer. We often see uncertainties, daily uncertainties in data around 5% or so, not uncommon, and often due to the installation, maintenance, and the data acquisition. You can get within 2%. What does that mean? So if you're calculating your plant output on the basis of that data, if you have a plant expected to produce 10 megawatt hours per hour, and the PPA rate will say, $100 per megawatt hour, so 10 cents per kilowatt hour, then, and it's coming down now, but of course that was the case not that long ago, then every 1% in uncertainty in what you've measured as the incoming irradiance actually costs effectively about $1,800 per month. So it's fairly clear that actually by fitting better pyranometers and better data acquisition, you can very easily get the cost back in a couple of months by the improvements in the measurements. So that's it. We're just about up to around 15 minutes or so, I think. So do you have some questions?
Very good, Clive. Thank you very much. Yes, there are some questions, and we just will take some more minutes to to have these. So thanks again for a very interesting presentation. The first question I'm reading up is the following. Is further averaging of recorded data to 10 or 15 minutes recommended?
It depends on what you want it for. If you're doing a sort of, shall we say, resource assessment or something like that, then you are really probably don't need more than hourly information, hourly averages, and then making it into days and weeks. However, when you're looking at performance measurements, real-time performance measurements in the plant, and then if you're going to report that every 10 or 15 minutes, then you should have at least 10, 15, shall we say, sets of data that's behind that. So you would have 1 minute averages and then average that over the reporting time, say the 10 or 15 minutes.
Clear, thank you. Another question, Clive. Give me 1 second. Does Kip and Zonen assume that pyranometers, 1 second, so I'll put on my screen again. Here you go. Does Kip and Zonen assume that pyranometers are degrading over time similar as PV modules? And if yes, what is the degradation mechanism? What can you say about it?
No, it's not similar. One of the reasons is because the degradation rate on PV modules is extremely variable, and largely it is not so much the module technology, it is actually the condition of the glass. Mostly we're not talking about polycarbonate phase ones now because they degrade very rapidly. So we're talking about glass, and it depends on the coatings that are on the glass, anti-reflection coatings, anti-soiling coatings, things like that. And cleaning regimes, how it's scratching the glass and things like that. So actually degradation of the glass on PV modules is usually quicker than it is of the actual semiconductor layers, whether it's thin film, polycrystalline, whatever. In the case of the pyranometers, the main thing that causes a change with time, assuming it's kept clean and maintained, is the black coating. The black absorber coating that you see on the surface gets very slightly less black with time. It's very, very slow, and you can't see it even after 20, 30 years. And it will be a maximum, for instance, in our secondary standard ones, we quote a maximum of 0.5% per year. It's typically less, but that's why we recommend recalibrating every 2 years, because potentially it might change up to 1% in 2 years, and if you've got, you can have an expected daily uncertainty of say 2%, then that starts to become significant after 2 years, a 1% change. So that's why we recommend recalibrating every 2 years. But the change is very, very slow, and it's not more than 0.5% a year. It's usually much less than that.
Well, Clive, that is for your pyranometers. Is there a big difference between different manufacturers in degradation, as far as you know?
There is some slight difference. Basically, some of the, or shall we say, from the high quality manufacturers, it's relatively similar. However, some of the very cheap instruments, they actually just use a very simple spray-on black coating, like a black paint, and that degrades much faster, particularly with the UV from the sun. What we use doesn't actually quite look like a black paint. If you use a magnifying glass, you will find it looks a bit like black sugar, so that it actually absorbs radiation from all directions. So generally speaking, yes, a good quality one will be similar, but a lot of the cheaper ones do degrade faster.
Clear. Thank you, Clive. Another question. So KIP offers different pyranometer outputs. It seems there is a trend to use digital output, is the question. So how can the output milliampere millivolt Modbus influence the measurement?
Okay, so in the case of if you don't have, shall we say, a smart one, if you just have the raw output from the detector, you've got a signal on a bright sunny day is going to be about 10 millivolts. the sensitivity is about 10 microvolts for every watts per square meter. So if you want to measure on, say, a cloudy, dull day when you might have 300 watts per square meter, and if you want to measure that within 1%, 3 watts per square meter, that's going to be a signal of about 30 microvolts. And if your data logger and analog to digital converters can't actually resolve that with a low uncertainty, you're not going to be able to actually measure, shall we say, accurately enough. So most industrial sites either take 4 to 20 milliamps or 0 to 1 volt or 0 to 10 volts, and more now are using an RS485 digital signal with Modbus. So our smart ones that have got the microcontrollers inside they have very accurate 24-bit analog to digital converters for the signal from the detector. Everything is processed in the digital domain. The sensitivity is stored, it does temperature correction, and it then actually calculates the irradiance in watts per square meter. So there are no additional errors involved. It's updating the output every second, so it's just waiting for the Modbus system to poll it and say, sensor number 23, send the reading in watts per square meter. You also get the internal temperature, the supply voltage, its calibration factors and other things like that as well if you want it. So you just take the digital value directly in and store it. Now you still want to of course do averaging and things on the data, but there is no degradation of the actual measurement. It also has a digital to analog converter back on the output, so there is a 4 to 20 milliamp signal as well for people who don't have a digital input. But again, a lot of the relatively low-cost industrial 4 to 20 milliamp controllers, data acquisition systems, don't actually have that good performance either. As I said, they will probably only give you an uncertainty of around plus or minus 5 watts per square meter. So, so that's one reason why people are going to the digital ones. The other thing is, of course, they're all addressable. So if you have a large number on the plant, they can all be daisy-chained onto one cable back to the control room. And you just say, number 21, send the reading, number 22, send the reading. So it saves on cabling costs.
Makes sense. Talking about size and multiple pyranometers, Clive. One question is, how many pyranometers do you recommend installing for a typical 50 megawatt plant? So I understand this very case dependent, but what can you say about that?
Yes, it is site dependent, and typically you would have one or maybe two on two sides of the plant that are horizontal, because the horizontal ones are effectively the reference. That's what you're comparing with meteorology data, models, and satellite information. Then the tilted plane of array ones are the ones you're using for calculating the outputs and the performance ratios. And on a larger plant, when you have partially cloudy conditions, it takes time for the clouds to transit across. So you've got shadows going across the plant. And that's when you start to need to have additional tilted ones. So also, because you get issues as you go further back in the arrays, the ones nearer the front tend to be seeing more radiation than the ones further back, particularly when the sun is low. And so typically, yeah, it is something like around 2 or 3 pyranometers on, say, per 5 megawatts, something like that. Typically on a 5 megawatt plant, you would have a horizontal one and 2 tilted ones, because you need some redundancy as well. There is also an issue of course, you might want to duplicate redundancy because periodically you're going to send them away for calibration, and then you don't want to lose the measurement. So there may be, shall we say, a second backup set that is used or goes around sites to replace ones that are being calibrated. But so it is rather site dependent, but basically yes, the bigger the plant, the more you need, because of essentially you get more variation in the radiation that can be seen by the panels at the back, at the sides compared with at the front, and the transit time it takes for clouds to get across, which could be many minutes on a large plant.
Yeah, makes sense. So extrapolating your answer for a 50 megawatt plant, this could easily be between 20 and 30 pyranometers or more.
Yes, by the time you include redundancy and backups and things, yes, it could be 20-ish, something like that, yeah.
Clear. Clive, thanks a lot. There are further questions which I'll try to address to you by email, and I also want to encourage participants to send us emails afterwards. But there's one more question for Pablo, so I'm going to mute you, Clive, and unmute Pablo again for a last question. Thanks a lot so far. Are you still there? And can you hear us?
To me, yeah, I'm here.
Okay, perfect. There was a question earlier we saw from the poll question that 35% of, or at least the people in the webinar, but that's extrapolated to the Japanese market, uses only Nedo. With the impact of well, that you explained. Do you see a trend? Are let's say either international or domestic solar developers, lenders, learning and let's say not using only Nedo? Is there a trend, and if so, which?
Yes, I have to see that that there is a trend. Now Metanorm is getting more accepted. More people know it here in Japan, and there are also other databases that are coming to the market, worldwide players that started to focus in Japan. I don't know if I mentioned maybe briefly, for example, SolarGIS in Japan has around 10 years track record. In Europe, this number is longer. They have a more historical period. So they are moving to Japan. Other databases like 3-tier from Vaisala, they are also moving to Japan. So people abroad is coming here. More international players are coming here to Japan as well, and they are bringing their, I wouldn't say only their knowledge, but also their experiences. And all these things is getting shared, it's getting mixed. We see Japanese banks with international investors. We see Japanese investors with international banks. We see international EPCs, Japanese EPCs, a little bit of everything. And yeah, of course there is a trend. The market is evolving, and I hope this also helps in moving forward with with this trend.
Yeah, okay, so that sounds like a good development for the market. To round off, because we are well over time, I want to thank again Pablo and Clive for sharing their expertise. You will be meeting people and experts like Pablo and Clive at the conference in 3 weeks in Tokyo, Solar Asset Management Asia, as mentioned before. If you have any questions about the webinar, you want to get in touch with the speakers, you have specific questions, or you have questions about the conference, feel free to reach out to me or my colleague Saori-san. Emails are on this slide. We look forward to possibly meet you in Tokyo, where we will discuss these topics and many other relevant topics further. You'll receive an email with recordings of this webinar afterwards, possibly today European time, so you can look and listen back. We look forward to be in touch with you and possibly meet you either in Japan, Tokyo, 2 and 3 of June, or at any of our other events in the near future. Thank you very much for listening, attending, for your participation, and I wish you a great day or evening wherever you are. Bye-bye.